Well, thank you very much for the kind introduction, and thank you to the organisers for the invitation to come to the meeting and speak, and the wonderful hospitality that we've all enjoyed, and I've eaten far too much food, so, which has been terrific. I'm talking today on determining compatibility in solid organ transplantation, and this is a fairly large topic, and as Fiona sort of indicated, through the Virtual Crossmatch project, we kind of brought everybody together a lot more and had a lot more dialogue with our clinicians in our labs around what actually they wanted to have for compatibility and what defined the virtual crossmatch. This opened our eyes in terms of what the clinicians were thinking, and the question of, like, you really think that came up a lot, and trying to explain how antibodies worked. But it was historically defined compatibility as a CDC negative crossmatch at time of transplant, and that's basically physical or virtual really, and that's what is sort of accepted as the main term. But we've done a redesign, or we're in the process of doing a redesign of our organ allocation algorithms for our deceased donors, and it's focused on compatibility beyond the crossmatch. And I think this is one of our challenges, is that we now are expected to predict post-transplant sensitisation and outcome, because we have the tools to do that better than we have before, and there's a lot of publications on this. So you've got, not only do you have to have a compatible cross-match, but you have to also look at the risk post-transplant. And obviously HLA antibodies are the critical element for compatibility, but also HLA typing at the allele level is very important for the degree of mismatching. So as Fiona said, we've got an extensive toolbox to detect and characterise antibodies, but it's a lot of information, and it's not always clinically significant, and it can be very challenging and obviously very costly, which is a real issue for us because we are government funded in Australia for all transplantation, and we have to convince governments that they need to pay more money, which is not easy. We did get away with that with the virtual cross-matching, but it was a tough ask. So compatibility is largely interpretable, and obviously there are lots of differences. It's not one size fits all. Organ type, there's clinical drivers like size, urgency, HLA expression, which is different across the different tissues. The donor type, deceased or a living or exchange donor as well. In the renal setting, we have a large kidney exchange program across Australia and New Zealand. And compatibility, I think the labs see this a little bit differently, from an immunological perspective, but clinical has more elements. And the clinical units have different appetites for risk, is what we've discovered. So what one unit will do to cross a low-level DSA and manage that, another unit may not want to do that, depending on the organs and different things. So I always like to say that transplantation compatibility is like an orchestra. There's a lot of instruments, but none alone are the music. And that compatibility is a challenging concept, a complex and challenging concept, and we know what's bad, but we don't always know what's optimal, and I think that's one of our ongoing conversations. So obviously the bad elements are HLA mismatching, it's a strong predictor of poor graft outcome, donor-specific antibodies, so antibody-mediated rejection, which can be acute or chronic, post-transplant de novo, DSA, reactivated DSA, or HLA mismatching, which has caused that. And we want to identify and control those elements. So as I said, HLA antibodies is critical, and identifying them accurately is the most critical step. They have to be detected and defined in detail for all loci. Peak and current sera, peak has kind of gone out of fashion of late, but we still have varies in significance depending on the transplant unit. Single antigen bead assays for HLA antibodies are far more complex HLA antibody data and require a lot of interpretation. And we use HLA antibody data extensively, but the context can be different for solid organ in different settings for pre or post-transplant. So I just want to have a word about cutoff. So when we did the virtual crossmatch project, most of the international experience was to take the antibody level very low, and this was not a popular thing in Australia because they had CDC, they understood that Luminex detected antibodies below the CDC level of sensitivity, and that we wanted to be able to maintain some of the options for transplant, not deny transplants for all patients, by looking at low-level DSAs and not excluding these. So we've established cutoffs that were acceptable to everyone, and I'm sorry, I've got some Immucor values in here as well, between the 1 lambda and Immucor, and these are kind of the guidelines for that. It's a little higher for the heart and the lung because their patients can be more urgent, tissues express HLA differently, and obviously below those MFI values, there's a DSA assessment that is done by the labs, which is the question Paul asked, and they do give a report on low-level DSA activity, and the clinicians can decide to proceed or not for that particular patient. We use unacceptable antigens in our new organ match system as the cutoff. These cutoffs above anything above 6,000 or 4,000 MFI will be listed as an unacceptable antigen, but also other HLA can be listed if they're part of an antigen group or previous transplant or part of an eplate group. So antibody negative previous mismatch is a clinical decision because we have a lot of dialogue about whether antibody negative previous mismatch should be excluded or not. And that depends on the unit's risk. All the cutoffs are agreed. There's a lot of dialogue, as Fiona has said, between the units and the labs now, and they don't want to limit transplants, and so this is an ongoing discussion that goes on all the time, and also not accrue a whole lot of highly sensitised patients on a transplant waiting list if it was too low. But the reality is that most people don't accept DSA above 500 MFI when you do the MFI. When you do the report and report the low-level MFIs, even though they want to see them, they generally don't accept the organ offer for those patients. So that's a little frustrating at times for the labs. The single antigen beads are extremely valuable, this assay, and I always say we've got a bit overexcited with single antigen beads. They're highly sensitive and specific, and they've identified HLA antibodies to all the loci, which is something we couldn't easily do prior to the development of these assays, and especially for class 2. They're consistent reactivity within a lot, but there are a lot of issues, and it's important not to ignore these. So, we all know the manufactured beads, so it's not the same as what's expressed on a cell. The assay is not quantitative. There's variable a number of molecules per bead. But the MFI, unfortunately, is a numerical value and seems to imply this. Locus expression is not a representative native cell. They can be denatured, so false positive, in the manufacturing process, which I know the companies are working to fix. And antibodies that have shared eplets can have artificially low MFIs because it can spread out across the whole bead panel. And there are some lot-to-lot variations. Bead pattern behaviour is something I don't think we focus on a lot, but it does need to be noted. Beads will have the same behaviour within a lot time and time again, and you can often get good information. The kinetics of the binding is not well described. Antibodies in excess or HLA molecules in excess and prosome immune complexes. And the bead sort order can be different to the immunising HLA antigen. So it's positive for different beads just because of the number of molecules across the beads or the eplets or how the binding is working. So there are a lot of complexities, and there's been a lot of papers that have published information about being careful on this space, and so we can't assume these results are directly correct in that way, and we do need to tease it out, and we do need to use, we use a lot of MFIs for all parts of transplantation matching and compatibility assessment, and it's difficult to know what to report on a report when you've got these positive reactions and you've got these false positive beads. And it's a clear result in the test, but you have to explain to the clinician that actually it's not really, it's a spurious bead reaction. And labs, it's very hard to get consistency across all the labs to report those and how they so we do need to have a really good deep dive in to ensure those results are correct. I think the other thing we've learnt in the virtual cross-match space, and certainly with more dialogue with our clinicians, is how they see the HLA single antigen bead results. They really just want a positive and negative answer for a cross-match. They don't want to have to nuance the ins and outs of all these weak antibodies for their patients. But why isn't the MFI quantitative? And they do understand the shared eplet concept, but not why the single antigen bead is negative for some of the beads with the shared eplet. So you'll get a pattern where you can find one eplet, and then you don't see it with all of them. And how to remove some of the DSAs for highly sensitised patients, to delist them as unacceptable and open up transplant options. And they say to me, well, you seem to sort of tell us one thing one day and then change your mind and tell us something else, but often we're talking about different loci. And unfortunately, from the clinician point of view, they see all HLA as the same. And I think that's one of the challenges in explaining that they have different function, and that's what's important. Just a note on the denatured beads, the group in Adelaide, Rory did a nice little study with the team there in Lucy's lab, and they looked at some of these peptides lost in the manufacture. Do you ignore them? But if you assume that all the molecules are denatured, what if it's only partial? What if only some of the molecules are on that bead? And B8's the best example I can think of this, where it might be weakly reactive, but you might be finding a real antibody. It's just that some of the beads are denatured. Sometimes it's a spurious bead, sometimes it's not. And I think this study that they did in Adelaide with the absorption and elution showed that the B8 antibody was real, but it was weak. And it only worked in the flow cross-match with homozygous cells. So I don't know whether that's really a phenomenon in terms of partial denatured beads, because peptide binding has different kinetics in its own right. And so it's a possibility, but we tend to think of it as it's denatured, the bead's a dud and it's a spurious result. So maybe that's not quite right. As I've said, the bead patterns are important, and each bead is an independent reaction. The assay is not a single test. That's taken a little while for our clinicians to kind of get this thinking. And we do need to know how each bead behaves in the single antigen bead assay, because it can just be specific for that bead. And if they have the same HLA antigen group, each bead it's an individual construct of that HLA molecule to that bead. So the order of the single antigen bead relates to the MFI, which is based on the molecular density of the bead, not necessarily the importance of the antibody. So the higher MFIs can be a bit misleading sometimes when we report these, and I think it's important to do that analysis. In this example here, which is that organ match system, this is how the system reports. It compares the donor and the recipient HLA type, and you look at the sort order for the A2 eplet was an A2 mismatch in this particular case, but obviously all the B17s, all the 57s and 58s came up first, and those sort of results do need to be explained to our clinical teams. The other thing is that, and I think it's often overlooked, function is important. I keep saying to everyone the F word. You've really got to understand function. All HLA molecules are functional, and the expression relates to function. It's different across the different loci. This is not a single entity, and the clinical implications for solid organ transplantation and HLA sensitisation will also differ because of the different functions. C-lockers exhibit a low expression, but that clinically significant, perhaps not. But you know, if you had a low-level MFI DQ, you might be a little bit more concerned, and that could be important. So we do need to consider function in analysing the results. And there's a lot of papers here, and Annette Tambur will tell you that DQ is a very special molecule, and she has published widely on this molecule and how it behaves, and the heterodimers and how they switch. And I think it's interesting to note that mismatches can lead to more unacceptable antigens and greater sensitisation. But DQ in particular is an early expressed post-transplant, and that's why we do see a lot of antibodies quickly. The other topic is epitopes or eplets, and this is a huge topic. I'm not going to go into everything with this, but just that eplet analysis can make sense of the antibodies, and obviously it's the functional target where the antibody binds. Not all the eplets that are described are verified, many are theoretical, and there is an eplet registry which is really useful information, and I definitely think it's worth looking there before you make the final analysis. And it does work well with serotypes comparing function. But as everyone will tell you, there's a lot of papers that, you know, eplet immunogenicity needs context. And the HLA type of the recipient determines the immunogenicity. What's the effect of the HLA alleles in the donor? So although the differences can be seen immunologically, the degree of difference can vary. And obviously the papers out of the Netherlands have been quite informative about how immunogenetics, the immunogenicity differs for each donor-recipient pair. So, and you do have to do this each time. So this is the René's diagrams that he's got here, but the important thing is the structural residues are seen by different HLA differently, and they're more prominent for some than they are for others. So there isn't really a single eplet that's going to be a danger eplet, I think. I think it's always related to the HLA type, and if the population in Australia, we have a highly blended population, everybody's from everywhere, it's really, the HLA types are quite different and quite diverse. And when you have different diverse populations, then you can have very different immunogenicity for some of the mismatches. I think that a lot of the published data is based on not such diverse populations, so you just need to be a bit careful in that. The conundrums for this is when the single antigen bead shows eplet positivity to the allele other than the immunising allele, which also shares the eplet, so what do we report in that setting? What do you do when the single antigen profile shows an eplet but not all the beads are positive, and should they be a UA? Rob Lewinsky suggests not unacceptable antigens for the ones that are negative, but to monitor these. And obviously, as all eplet positive HLA molecules equally clinically significant in every donor-recipient pair. Eplet loads, the other thing, we tend to count things, add them up and say this is bad. And so this is, DSA are more likely when there's a large number of eplet mismatches. And obviously the number of different eplets between donor recipients, poor outcome with more DSA. So, but what's the cutoff for the load? How many eplets is bad? We don't know. And there are papers that have actually discussed this about eplet load and de novo DSA, showing that there is an impact, and obviously to use them for equally, the converse is that we should be careful about how we use that information because it's not well defined. And so I think there's a lot of work to do in this space. I would like everyone and encourage everyone to participate in the international workshop eplet projects, because I think we really need more diverse populations to get this data right, and there's a lot of questions to be answered. So please look on the website for the 19th International Workshop. Professor Tokunaga's here, he's been talking about this, but this particular part of it is something for solid organ transplantation is critical. We use a lot of additional assays to confirm HLA antibodies, and obviously you can use an alternative kit. Both the kits are good, they have different ways of doing the analysis. It can be costly to use two kits, but we generally see the same reactive pattern. The absorption and elution process that Rob Lewinsky and Rob Carroll, who's in the audience, have worked through and worked up, that's been really useful in some settings to show true activity, especially because you can then you use a native cell to actually do the absorption, and that can be very, very informative. But you still need to do another single antigen bead test, and that is costly. C1q and C3d assays, these kind of go in and out of fashion. Thought to identify complement binding antibodies, which are more clinically relevant. I think it assumes that the antibody isotype is fixed and doesn't change. And I think from what I feel is that antibody production is a dynamic space, and you don't, if it's an IgG3 or an IgG4, it's not going to fix a lot of complement, but if it suddenly, it might change if it's re-challenged. So I think we can't assume that that's going to always be negative. Or clinically not fixed complement and always be compatible, I should say. Serum dilutions we don't do a lot of, largely because of cost, but we do it in our transfusion setting because there's a real culture of getting the endpoint of the antibody, and we do have some really interesting data for some of our FNAIT patients in that space. We do see quite a difference in the antibodies and how they tailor off, but these are all pregnancy-induced antibodies. It's a little bit different in the transplant setting, so we don't have a lot of data in that space. Surrogate flow cross matches, well, the advantage is the whole cell assay to confirm your antibody, and it's useful if you've got the cells. You could use a frozen panel for that, but you need to have, for highly sensitised patients, it's not useful because there's too many antibodies present. But it's a flow cross match, so it can also introduce another variable than HLA, which could be false positive for different reasons. So we do use this assay to tease out some of the antibodies, but and also just to be careful, cell lines are not a good target because they can vary in expression. Extended bead panels, are these going to give you really more information? I mean, I'm not sure. I think you get more allele coverage and the specificity can be useful, but you could use another way of doing that. And if you don't have a bead for that particular allele you want to look at, then how useful is it? So I'm not sure that that's really essential. High resolution typing of the donor is important, and it's not routine in Australia yet for deceased donors, but will come. And allele level typing is important for the eplet analysis and obviously to assess compatibility, or if there's allele specific antibody present. Allele level matching will need to include the serotypes though to be effective. And I think it's allele specific antibodies do exist. I feel that this happens when the recipient has a different allele of the same antigen family, and you will have to the donor, and you will see a allele specific antibody form in that setting. Molecular matching has a lot of press, and certainly people are keen for it, and high resolution typing, it seems like a good idea. And different ways of counting mismatches can show different outputs, and there are papers represented here which publish that. but I would explain that information. But I think there are risks with compatibility to directly compare the donor allele level HLA type and the recipient antibodies reported as an allele, and can be misinterpreted as compatible if not the same donor allele versus patient antibody, or incompatible if you're different alleles looking for an allele match. And it may belong to the same serological function group. So you just can't take the allele and the antibody allele description and match them. You do actually need to analyse this properly. Serotypes, we did a paper on serotypes with Kazu and Marcelo at the Stanford group, and obviously this was very useful. We have been looking at G and P codes, and I think Steve showed that in a talk yesterday, to look at the serological function and what is shared and what is likely to be a mismatch in terms of immunological mismatch, but it can be useful to identify compatible HLA alleles. Software tools, well, there's a lot of these. We have Emma, which is quite useful easy to use, and it can be useful to give you information. We have Perch as well, which can be useful to look at the peptide and other responses. It needs to distinguish between immunogenic peptides and non-immunogenic peptides. And I think, and as I've said, the G and P codes, which are on the IMGT database, are also very useful to be able to tell you if the alleles are within a cluster. So how do we determine compatibility? Well, there's a lot of stuff in there. And I think that's a lot of tools. And unless you have a very large budget and a lot of people and a lot of time, you can't use everything. We really need to define what question we want to answer and use the appropriate tool to answer the question, and not just test the patient for everything, because that can be really confusing in terms of the data and information you're giving to the clinical units. We should also not focus on one approach. We have some people who are just locked into eplets. That's all they want to do. They don't care about anything else, but eplets alone is not the complete story. And we need to be smart about the assays. In my entire working life, which is now a long time, we have had a lot of assays come and go, and we've had a lot of different sensitivities and a lot of specificity changes and other things. None of them are perfect. Everything gets to 80%. And I think it does need to be, critical thinking is important to get the whole clinical picture. So just some key points, and I'll finish in a second. Defining compatibility depends on the transplant setting, and that's important to think about. A no DSA, low-level DSA will cross, that can be useful. Beyond the cross-match and the post-DSA, post-transplant DSA is a future state. Imlifidase is an interesting thing. I haven't talked about this, but the negative cross-match, but I think Sarah's talking about this later today. It's a negative cross-match, but it's not no DSA. So I think, in that setting we have a negative cross-match, but there's actually a lot of DSA there. It's just not there at that moment. And the transplant pathway has a different risk profile, organ type, for deceased donors or living donors. We need to determine each patient's specific requirements for compatibility and the clinical unit's specific requirements for their degree of risk, and facilitate transplant by identifying risk but not excluding everything. So compatibility is not a fixed point. The immune system is always playing the music in that orchestra. We can quieten it down with some immunosuppression and lose some of the instruments, but the rest of them are all still going strong. So from that, I just want to say thank you and answer any questions.
Thank you, Rhonda. And now, please ask some questions, please.
Thank you, Rhonda, for the very nice and very thoughtful talk. I have a question about, for your renal patients, you have different cutoffs for assignments of antigens, which we do in my lab as well. But I noticed under your lungs that you only had one cutoff, and it seems to me that the stratification for thoracics would be even more important to say that Cs and DPs, we're not going to list them at all, instead of having one cutoff at 6,000. So what's your strategy for that?
So that was a diplomatic solution. Most of the cutoffs were diplomatic solutions. We had camps that wanted 1,000 and camps that wanted 8,000, and honestly we just had to draw a line in the sand and say this is what it's going to be. I get to be the bad person and say no. And it's hard, but I think we need data to convince people, and I think that's what we're gathering, through the virtual cross-match and certainly through the organ match, which is an amazing system, which we've been very fortunate from the OTA to fund us for. It really gives us the opportunity to get a lot of data together to be able to tweak this. And yeah, I agree, it needs to be tweaked. They're different. Lungs are very different to hearts.
Absolutely.
You know, like the lung environment, all the cell types. You know, I've worked in transfusion. We've had a lot of trial cases. I know a lot about the lung, you know, mixture of cells, and that is something that's it's really different in the lung space. But and largely in the thoracic space, they kind of do their own thing a little too. So it's sort of like a starting point. We don't use it. We use it as a starting point to say who you shouldn't transplant, perhaps. But even then, they might ignore that depending on urgency. Yeah.
Maybe it's just that the thoracics need a little more education than the renal.
Yeah.
Surgeon.
Now for the next question for this Dr. Yingnyot. Yes.
Hi, I'm from Bangkok. I'm a nephrologist and from the Thai Transplant Society.
Fantastic.
Thanks for the very clear lecture, and I believe that Australia and Thailand something very similar in terms of organ allocation. Especially we have a lot of disease donor transplantation like Australia. Now the question is that we begin to embark on the virtual cross-match, and I don't want to, you know, learning from trial and error. And you say that there should be optimal way to do the organ allocation. So give us some hint that what kind of technologies, optimal, not expensive one, and well, that is the most important for the clinician.
Yeah.
And the way that we won't go the wrong way, maybe from your experience.
Yeah.
Thank you so much.
We went with the most expensive option first, with a view to getting data to look at whether we could tailor that to make it use less expensive kits, whether the frequency of screening 4 times a year was important. It was largely because the clinicians and mostly the people on call with the registrars were used to getting a positive and negative result.
Yep.
And we had to provide confidence that a virtual cross-match compatibility result, because that's what it was going to be okay. We've been monitoring the data for the last 2 years. As Fiona said, we took a couple of years to implement it. We kind of got people off CDC trays slowly and showed them that the world did not end, and that it was okay, and that we had no higher frequency in post-transplant rejection at all, or unexpected antibodies. So it does take time, and it's very important to have a great dialogue with your lab and with the clinical teams, and to make sure everyone is well informed.
Yep.
I think we've had a separation for many years between the labs and the clinical teams. And I think that's what Fiona has alluded to, and it taught us a lot around having that dialogue together, and some of the surprises about how people were thinking what the test was telling them versus what we knew, and then trying to bridge it together. So yeah, I wish you well. It's a lot better. Virtual cross-matching is certainly a lot better. It can be a computer algorithm. There's a lot of good things for it. It's just the confidence in terms of making sure that you've got all of the risk factors and you've defined them. Yeah.
Great. I hope this message go to Nattiya, the chairman of, and also the Thai Red Cross organ allocation. Yeah.
You have the best people here. It's okay. Thank you. I think we'll finish there in time.
Okay,
Yeah.
for the times. And thank you, Rhonda, for the marvelous presentation.